Today we're going to talk about the second set of simple machines. We talked about the lever, the wheel and axle, and the pulley the last time we were together. So today we're going to talk about the incline plane, the wedge, and the screw. And just as a reminder, here are pictures of those. So the incline plane is like that roller coaster, the wedge is like the X, and the screw you can see going through that looks like some sort of a jack. An incline plane is useful in helping to move objects along, like a longer distance, but up vertically. So it takes the load off of the person, and the incline plane helps. So it's basically a flat surface that's set at an angle. And it doesn't have any moving parts. So you are able to lift that object up to that vertical height by pushing or pulling the load. The ideal mechanical advantage is found the same way as when we looked at the lever and the wheel and axle. It is the effort distance divided by the resistance distance. And in this case of this simple machine, the effort distance is going to be the slanted distance. So it is the 15 feet, while the resistance distance is going to be the height. How high vertically did you move that? So 4 feet. So to find the ideal mechanical advantage, you're going to take L, which is 15 feet, and divide it by 4 feet. And when you do that, you get 3.75. I would be perfectly okay if you left it just like this, 3.75. You do not need to write it in this ratio form. The actual mechanical advantage is found by taking the resistance force and dividing it by the effort force. So for this inclined plane, the effort is 20 pounds. Sorry, you are pushing that cart with a 20-pound force, and the load, what's sitting in the cart, is 50 pounds. So the AMA is 50 pounds divided by 20 pounds, or 2.5. Now we can look at the efficiency of this inclined plane. So we take, remember, percent efficiency is the AMA divided by the IMA times 100 to get our percent. So it was 2.50 divided by 3.75 times 100, and we get 67%. So the mechanical, or the simple machines that we looked at last time, the lever and the wheel and axle and the pulley, they had a higher efficiency rate. They were up into the 80s, the ones that we looked at. And part of that is this inclined plane loses some of its efficiency because of friction. So you're pushing something up that incline, and there's some friction involved with that. The wedge just functions as a moving inclined plane. It tapers to a thin edge and is used for splitting or raising heavy bodies, or for tightening by being driven into something. So you might have seen a wedge used as like a shim when you are trying to level cabinets, or we recently replaced a toilet and we had to put a shim in there so that the toilet was level. Or you use it to split wood. That's another function of it. So this time, well, the IMA is found still the same way, the effort distance divided by the resistance distance. But this time it's not the slanted distance. It is the distance perpendicular to the height. So for this case, it would be 10 inches for the effort distance would be 10 inches, and the resistance distance is the width of that, which is 3 inches. So to find the ideal mechanical advantage, it would be 10 inches divided by 3 inches, or 3.33, or you could round it to 3.3. The actual mechanical advantage found just like the other ones, the resistance force divided by the effort force. And in this case, the wedge is pushing, like it's splitting something, and there's a 70-pound resistance, and the effort is 250 pounds. So we are pounding that in with 250 pounds of force. So to find the AMA, it would be 700 pounds divided by 250 pounds. The pounds cancel, so we have 700 divided by 250. So the AMA is 2.8. So the efficiency of this wedge would be the AMA 2.8 divided by the IMA, which was 3.3, and then you multiply by 100, and we get 84% efficient. The screw is the one that I kind of call kind of a pseudo simple machine, because it really is the combination of two different simple machines. So it really is just an inclined plane that's been wrapped around like an axle. So you can see the picture where it's wrapping that inclined plane around the pencil and then creating what would be the threads. So the wheel and axle is used to create that rotary motion. So we're going to turn that screw to drive it down into the wood. So the thing that we need to know about this is this idea of pitch, and that is the distance between two threads. And so that stays consistent all the way through. So the distance between any two threads is the pitch. So some properties of the screw is it changes rotary motion into linear motion. So we're going to turn it, but we're really trying to get it to go either vertically or horizontally when we're screwing something in. It's used as a threaded fastener, so once it's in there, it's not coming out because it's threaded down into that wood. It has a large mechanical advantage. However, it also has a large amount of friction loss. So let's take a look at how do we identify a screw. Well, you know what it looks like, but here are some properties of it. So this information over here, this thread information, tells me something about this screw. And so when you go to buy screws, that you will often see that information. So the first number, this 1/2, is the diameter of the screw. 13 is the pitch, like how many threads per inch. And then the NC tells me if it's coarse or fine. So here you can see the pitch is right here. It's the distance between these two threads. The diameter is of the screw. The effort arm distance is the length of the wrench if we're using a wrench to turn that. So we're actually, the effort's coming from the wrench, not the head of the screw. So this is important. If it's 13 threads per inch, then the pitch is 1/13. So 1/13 of an inch is the pitch. How far will a screw with 13 threads per inch move linearly if turned one full rotation? It's going to go 1/13 of an inch. So when you turn it, it's going to go the distance between those two threads, which in this case is 1/13. The ideal mechanical advantage is the effort distance divided by resistance distance. So that should look familiar. So the effort distance is one rotation of the effort arm. So if we're using a wrench, we're going to find the circumference of that. While the resistance is one rotation, linear distance traveled during one rotation of the effort arm. So it's the pitch. It's how far it goes with one rotation, which is the pitch of that screw. So here's a kind of a simplified way to find IMA. It's the circumference divided by pitch. But you have to remember it's the circumference of the effort arm, whatever it is we're using to turn that screw. And we know circumference is 2 pi r. So what is the IMA of the screw above if effort is applied by a point or by an 8-inch long wrench? So we need to find the circumference of that wrench and then divide it by the pitch of that screw. Now remember, the middle number is the pitch. So this is 20 threads per inch. So it's 1/20 would be the pitch. So we're going to do 2 pi times 8 inches over 1 inch per 1/20 inches. So when we do that division, the inches are going to cancel. 2 times pi times 8, and then divided by 1/20th, or that's like multiplying by 20. And so we get 1005.31. You do not need to write it in scientific notation. This number is perfectly okay. And you could have rounded to that to 1005. The actual mechanical advantage of the screw is, so we're able to put 35 pounds of force on that wrench when we turn it, and the screw is resisting at 1,200 pounds. So we have 1,200 pounds over 35 pounds, and so we pounds cancel. So we're left with 1,200 divided by 35, which is 34.29. Now remember, our ideal was 1,005, and our actual is 34. So when we go to efficiency, this isn't going to be nearly as efficient as all the other ones that we've looked at. So remember, it's actual divided by ideal times 100. So it's 34.29 divided by 1005.3, and then times 100. So when you do the math, this is only 3.4% efficient. But remember, we talked about how there's so much efficiency lost to friction, because that screw is fighting back as it gets turned into that wood. This is a compound machine. This bicycle is an example of a compound machine. We've got some wheel and axles going on. We've got some levers going on. So when we have a compound machine, it's just simple machines that are working together to perform a task. And when we calculate the mechanical advantage of a compound machine, we just take the mechanical advantage of each individual simple machine, and then we multiply them together, and that gives me the mechanical advantage of the compound machine. So all the clip art came from Microsoft, so that's our resources there. So what you should do now is complete the Simple Machines Part 2 practice problems. You should have enough information now to do that, and so that's what you need to work on next.